Hello everybody, this is Sushrut and today we are going to discuss about connection between automata theory and number theory. Number theory is abstract mathematics. It delves with the properties of numbers itself. But what we are more interested about is how machines can decode these properties. We do this by using the simplest machines like a finite state machine which generates automatic sequences. An automatic sequence is a well-behaved sequence, but it lies somewhere between order and chaos. Somewhere like that it's going to follow a set of rules, but you can't predict what the next element is going to be. That is what a finite automata sequence is. In a more formal way, automatic sequences are basically a tuple consisting of finite set of states, alphabets, transition functions, initial state, output for alphabet, and the output function. Suppose you input a word into the finite automata. How does it process it? It basically converts it into the base K representation. Then it starts from the initial state Q0. It reads the digits from the MSB to the LSB, which is the left to right. Then it recursively calls the transition function, goes on to the next function till it reaches the final state, and then it applies the output function tau to obtain the finite automatic sequence. This is a famous example of counting the number of ones in a binary representation. And this basically shows if a number is divisible by 2 or not. And that is how you can see how we are connecting number theory to finite automata. As you can see, we have a finite automata constructed here and how numbers are transitioning from one state to another on the basis of inputs. Some of the first people who thought about this connection were Bucci and Pressburger. So Pressburger thought of state elimination and he described some arithmetic sentences in this way. But Bucci thought of finite state automata and moved forward. He thought of additive basis. So basically, what it says is that if there is a set of numbers, all natural numbers could be written as the sum of at most h elements from the set S, then that set is an additive basis. For example, we have a set of odd numbers, S is equal to 1, 3, 5, 7, and so on. You could take natural number, example 6, and you could represent it as the sum of elements 3 plus 3, which is 2 elements. You could take 8 and you could say, okay, 1 plus 1 plus 3 plus 3. That's 8, 4 elements. You may think, how is it useful in automata theory? Well, if S can be recognized by a finite automation, this means that it forms an additive basis. We can compute the bound and we can compute the minimal order. It's very important in algorithmic analysis of analyzing sets of numbers that are represented in a structured way using automata. For example, let's consider a set S of natural numbers divisible by 3. So we have 0, 3, 6, 9, 12. Let's represent them in the form of binary. You get 0, which is 0, 3, 1, 0, 6, 2, 0, 9, 1, 0, 0. Now our finite automata reads the digit from the MSB, which is left, to LSB, right. We have three states, Q0, Q1, and Q2. Q0 is basically 0 mod 3, which is basically remainder is going to be 0. So when you get 0, go back to Q0. When you get 1, go to Q1, which is 1 mod 3, basically 1 remainder. If you get 2, go from Q0 to Q2. Similarly, we can see the other ways of what input goes into which state and which state does it transition. Now that we have seen divisibility, let's move on to a more complex property of numbers, which is arithmetic progression. Let's take an example of 5n plus 3. As it is evident, we are multiplying it by 5 and adding 3. That means we must divide the number by 5. And if we get the remainder 3, it is going to be a part of our arithmetic progression. That is how this works, where you get the new remainder is equal to current remainder into 2 plus input bits mod 5. This is the finite automata for the arithmetic progression 5n plus 3. Let's test if n is equal to 3 is a part of the arithmetic progression. Convert it to binary representation 1 1. Start reading from the MSB. So read 1. You compute 2 into current remainder, which is 2 into 0 plus 1 mod 5. You get 1. You move to B. Now you input 1 into B. You say 2 into 1 plus 1 mod 5. You get 3 mod 5, which satisfies our arithmetic progression. So you move to state D, and hence 3 belongs to the arithmetic progression. Can prime numbers be represented by finite automata? This has been an open question for a long time. The probabilistic model suggests that if you have n numbers, then there is a 1 in a log n chance that that number is prime. But this is not enough for it to be recognized by a finite automation because it is too irregular. But this brings us to the question that how can we prove that a set of integers is non-automatic? Hence, we use pumping lemma. So we assume that a finite automation recognizes prime numbers, and we assume that any prime number p can be written as w1, w2, w3, and w2 can be repeated to form new numbers. If primes are regular, then w1, w2 to the power p, and w3 must also be prime. But by Fermat's theorem, we find that w1, w2 to the power p, w3 is equal to 0 mod p, which makes it composite and it's not prime. So this brings a contradiction, and this says that primes do not form a regular language and finite automata cannot recognize them. Let's get more complex. Expansion of algebraic numbers and how it can be recognized by finite automata. Cobham's theorem suggests that if a set of numbers can be recognized by finite automata in two different bases, then it is going to be periodic. For example, 1 by 3 is a rational number, which can be represented as 0.010101, which is a fixed pattern. But an algebraic number root 2 has no fixed pattern, and it cannot be recognized by finite automata because it is not periodic. Hence, we use p-adic automata. It helps in analyzing expansions of numbers in non-standard bases. For example, if we have 5, which can be written as 1, 2 in the base 3, we can write it as 1, 2, 2 from the right. This is all about number theory and automata. Thank you. Thank you.